Hey guys, what's up? Welcome back. Suppose I asked you to find a target number in a sorted list. Now, in the previous video, we saw a linear search where we would begin at the first element and then check the values one by one until we find our target value. But since this list is sorted, do we really need to check every single value? No, we can do much better. So in this video, we're going to learn binary search. Binary search compares the target with the middle element and then eliminates half of the remaining search space after every comparison. We'll first understand the idea, perform a dry run, walk through the code, and examine what is stored during execution, and finally derive the time complexity. Before we begin, always remember binary search only works correctly when the data is sorted. Okay, let's first take a quick look at the code. This code is in Python. Here you can see the binary search function, and right here is where we call the function. So as you can see, our binary search function takes four parameters: my list, target, low, and high. My list is the sorted list in which we are searching. Target is the value that we want to find. Low represents the first index of our current search window, and high represents the last index of our current search window. So, together, low and high tell us which part of the list we are currently searching in. We are using a recursive version of binary search. That means the function can call itself with a smaller search range. And then we'll understand each line properly after completing a dry run. As you can see, once again, I have divided the workspace into three sections: storage, output, and dry run. Storage section will show the variables that exist in the storage of the computer. Output section will show the last output that the computer will show us, and then the dry run section will show us the process through which the algorithm works. Okay, let's get started. Here you can see we have L, which is the list, sorted list. So it has 8 elements: 1, 4, 9, 10, 15, 32, 83, and 90. And our target value is 32. That means we're looking for 32 in the list L, right? So my pos is actually function call to binary search, and then I'm sending out the list, the target that I want to find, 0 as the starting index, and then len L minus 1. So length of L is 8 minus 1 is 7. So at the very start, I'm sending out the very first section of the list, which is the whole list, right? So in the dry run, our first function call is right here. Binary search, once again, is L tar 07, right? So my list is going to be L, correct? L, the argument L goes to the parameter my list. So my list will have 1, 4, 9, 10, 15, 32, 83, and 90. And then target will have the argument tar, which has the value 32. And then my low is 0. And then my high is 7, right? Okay, let's get into the function. So this is my base case. If low is greater than high, return -1. So you're essentially trying to say if the list is empty or if there's no more elements to look into, you return -1, which is not true, right? So we're gonna skip this if block and then we're gonna go to a mid. So mid in here is low plus high divided by 2. So this is an integer division. We're going to skip all the decimals. So 0 plus 7 over 2, right? So skipping all decimals, this is going to give me 3. Correct? So now my mid is 3. Now I have the 3 if statements, and then let's do the first if. Target, which is 32, equal to my list mid, right? So we know my list has indices 0, 1, 2, 3, 4, 5, 6, 7. These are the indices. And I'm looking at the value in the third index. So 32 is equal to 10. No, that's not true. So you skip this if block. Next if, is 32 less than 10? No. You skip this if block. And then you have, is 32 greater than 10? Yes, that is true. So we're going to do a recursive call, which is binary search. Again, I'm going to send my list because that is the list that I'm looking into. My target is the same. My target is 32. And then mid plus 1. So mid is 3, right? So 3 plus 1, 4, comma, and then high remains high, 7. So that means for my new function call, low becomes 4 and high becomes 7. Correct? So if you think about it, now I have to search in this part of the list from 4 to 7. So again, you go back to the function, you check the base case, is low greater than high? No, low is not greater than high. So now I'm going to solve for my mid. So my mid is 4 plus 7 divided by 2, right? Which is 11 over 2, which is 5. Again, this is a integer division. You disregard the decimals, right? So 5 comes in. Now I'm going to check my if block. If target equal my list. My target is 32 and then my list mid. Now my mid is 5, which is 32. Correct? So now I say, yes, this is it. So I'm going to return mid, which is 5, my current mid. So when you return, always remember you return to the place where you were called. So I return here. So this value becomes 5. Then this value becomes 5. There's nothing after that if block, right? After my call, my list target 4, 7. There's nothing after it, so that means this is what I'm returning. So I do return 5 again, and I return where I was called, right here. This thing becomes 5. So now that means since this is right here, this is 5, my POS becomes 5. My POS becomes 5, then my output will be value present on index my POS, which is 5. So value is present on index 5, which is true, right? We are on index 5. Now, quickly, let's get into a situation where the target is not in the list. Here you can see my target is changed to 33 and 33 does not exist in this list, right? Let's see what happens. So again, L is the list 149, 10, 15, 32, 83, and 90. And then target is 33. So we do the first call, binary search, ltar07. So this is what I'm going to write down in my dry run for my first call of the function. That means my list becomes 1, 4, 9, 10, 15, 32, 83, and 90. Let me write the indices 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then let's write down my low, which is 0, high, which is 7 right here, right? Size of the list -1. That's what we did for the call. And then my first check is low greater than high? No, it's not. Okay, I'm gonna check the mid. So mid is 0 plus 7 divided by 2. This is an integer division, so we discard the decimal places. This becomes 3. Okay, so mid is 3. So this one is my mid value. Okay, I'm gonna do my first check. Is 33 is equal to 10? No. 33 is less than 10? No. 33 is greater than 10? Yes. Okay, you're greater, so I'm gonna do my second call, which is binary search. Again, my list, the same list in which we're looking at, target, which is 33. And now my low becomes mid plus 1. Mid is 3 plus 1 is 4. And then high remains 7. Awesome. So again is low, which is 4, and high, which is 7. Is low greater than high? No, it's not. Okay, we skip this if block. Then again, we solve for mid. Mid is 4 plus 7, integer division by 2. So this becomes 11 integer division 2, which becomes 5, correct? So now my mid is 5. So that means now I am looking at this value. Okay. So I'm going to do my first check. 33 equal 32. Is that true? No, right? Okay. Is 33 less than 32? No. Is 33 greater than 32? Yes. Yes, it is. Okay. Since I am greater than 32, what I'm going to do is I'm going to do another call. So the other call that I'm going to do is, and I'm going to move my screen a little bit, is going to be binary search. And then again, my list. And we have target, which remains the same. And then now, since it is greater and my low will be mid plus 1, current mid is 5. So mid plus 1 is 6, comma 7. Okay, so low is 6, high is 7. My mid will be 6 plus 7 over 2, right? Which will give me 6, right? So now my mid is 6. Awesome. So now I'm going to do my 3 checks. The usual checks is 33 equal. On the 6th position now is right here. Is 33 equal 83? No. Next check. Is 33 less than 83? Yes, that's true, right? 33 is less than 83. Awesome. I'm going to do another call. So the call here is binary search, this guy, right? So again, I'm sending my list because it's going to remain the same. Target, and then my low remains low, so low is 6, and then high is going to be mid minus 1, so high becomes 5. So now is 6 is 5. First check, is low greater than high? Yes it is. So I get into my first if block. I return -1, right? So I return -1. As we all know and remember, we return to the place where we were called. So this -1 comes back here. This becomes -1. And then after this call, there's nothing to do in the function except return. So now this thing returns where it was called. So it becomes -1, right? From where we were called here. This becomes -1. And then coming back, this -1 goes back here. This becomes -1. So this is the value of my POS, -1. Awesome. Now we have the value of my POS. So what it's going to print? It's going to print value present in, and my position is -1, which is an index that theoretically does not exist. In Python programming, it does exist. So you can have an if check here. If my pos is -1, you can print value not found. Let's look at a few things that we should note about the function itself. If you look at the code, we know this is the base case, right? So that means when nothing is found or the list is empty, this is what is going to happen, right? We saw when we had a value which did not exist in the list, this base case was used. Another situation where it is used is when the list does not exist. So that means the size of the list is going to be 0. So low will be 0 and high will be -1, and then the base case will be true, and then we return -1 in that case as well. Moving on, this mid equation, low plus high integer division by 2, this calculates the middle index. We saw it in the dry run. Another way that you can see this is also low plus high minus low over 2. So this is another way you can see it. If you solve this, this actually gives the same equation right here. So this means low plus high minus low over 2. Now again, if I multiply 2 here and here, this thing will become 2 low plus high minus low over 2, which is high plus low over 2. So it's essentially the same thing as this guy, but you can see it in multiple ways, right? Next thing that you should look into is, we know that the list is in ascending order. Had it been in descending order, this function would have looked a little different. Think about it intuitively. If the target is less than mid, I'm actually moving the section towards the left side of the list. If it was in descending order, I would move it towards the right side of the list. So in descending order, these two things are swapped. So you move on the right side instead of the left side. This is another thing that you should definitely test out and run on your own, just to see. You can do the same list but in descending order and see how it works. Now let's understand the time complexity of the binary search algorithm. So we begin with n elements, right? So n is the size of list. Okay, we begin with n elements. So after each comparison, we're dividing the list in half, right? So we start with n, and then we go n by 2, either the left half or the right half of the list. And then we go n by 4, which is left sub half or right sub half of the list. And then n by 8, and then so on and so forth. And we keep doing it till our element is just that one element that we're looking at. Correct? Now, this n over 2k, I can show that how we came up with that as well. N can be written as n over 2 to the 0. This is n over 2 to the 1. And so on and so forth, right? That's how we got n over 2 to the k. So that means we took k steps to get to that one final element. Okay. And time complexity means how many steps did you take. So we're solving for k. So using this equation, let's solve for k. So n over 2k is equal to 1. Let's multiply both sides by 2k. Okay. I multiplied it. This and this cancels out. So this becomes n is equal to 2k. Now, if you know logarithms, when we solve for k, this becomes k log base 2n, which is our time complexity. So the time complexity is going to be O of log n for binary search. Okay, now let's look at the best case scenario. So for the best case, let's think about it. Where should the element be for the best case to happen? The element should be in the middle of the list, right? So the first try when we solve for mid and then target becomes mid, we just return the middle value. So that is my best case. So for best case, you only have one step, right? So the best case becomes O of 1, just checking for the middle value. This is the time complexity of binary search. O of log n for average and worst cases, and then best case is O of 1. So, to quickly recap, binary search works on sorted data. It compares the target with the middle element and eliminates half of the remaining search space after each comparison. In the next video, we will move from searching algorithms to sorting algorithms and begin with bubble sort. Thank you for watching. If you like this video, make sure to subscribe and like and leave on a comment. Have a good one.